You've heard it 1,000 times. The dark side of the moon. What do you picture? Endless black. A permanent night hiding something? Here's the thing that's completely wrong. The far side of the moon gets just as much sunlight as the side you see every night. About 2 weeks of daylight, then about 2 weeks of darkness. There's nothing dark about it, at least not in the way you've always assumed. But here's where it actually gets strange. At any given moment, you're only looking at half the moon. And that's because the time it takes to complete one full rotation on its axis exactly matches the time it takes to orbit Earth. About 27 days. That's why we always see the same side. That's it. No magic. The two speeds simply match. But we've actually seen a little more than half. The moon has a very slight wobble to it, like a spinning top just barely tilting side to side as it goes. Astronomers call that wobble libration. And because of it, over centuries of watching, we've actually caught glimpses around the edges, peaking at about 59% of the surface. Not 50, which means for most of human history, we assumed we knew the moon. Meanwhile, 41% of it sat there permanently out of view. And it's not just hiding territory, it's moving. In 1969, Apollo 11 astronauts left behind a small panel of mirrors on the surface. Observatories on Earth still bounce lasers off them, timing the return down to fractions of a second. That's how we learned the moon drifts away from us, about 1.5 inches farther every year. What is the moon actually? So let's back up. Forget the mystery of about light for a second. The most basic questions are, what is this other half anyway? And why does it look like it belongs to a different planet? Well then, let's figure it out. About 4.5 billion years ago, something roughly the size of Mars slammed into the young Earth. Not a graze, a full-on collision that melted rock and blasted a massive cloud of debris into orbit. That cloud clumped together into the moon. So logically, both halves should look the same. Nobody could check. Humans didn't see the far side until 1959, when a Soviet probe called Luna 3 swung around and snapped the first 29 photos ever taken of it. Grainy, barely holding together. Still enough to break the assumption completely. The land didn't match at all. The near side has those big, dark seas, smooth plains of old, hardened lava. The far side had almost none, just pale ground, mountains, and craters stacked on craters. Same origin, two different faces. Why? And the first thought that comes to mind is that the far side simply faces open space. So more rocks come from that direction, and it'd have gotten hammered harder. But that's actually wrong, because both sides get hit by roughly the same number of impacts over time. The difference is what was underneath. For hundreds of millions of years, Earth's gravity kneaded and flexed the moon, but only on the near side. Rock softened, and softer rock over time meant a thinner crust. The near side thinned out to somewhere around 37 miles thick, while the far side stayed closer to 50. When impacts hit the near side, that thinner crust actually cracked open, and dark basaltic lava came flooding up through the basins. Those are the seas you see every night, right next to the lighter, untouched highlands around them. The far side? Too thick to crack. There was no lava and no seas, just crater stacked on crater stacked on crater. 4 billion years of impacts sitting frozen almost exactly as they landed. So what about underneath? We know the near side of the moon rings like a struck bell because we've actually tested it. When Apollo 12's rocket stage was deliberately crashed into the surface, the ground rang for almost an hour. The physics are simple. It's bone-dry rock with absolutely no moisture to dampen the vibration. What about the far side? It remained a scientific blind spot. That is, until June 2024, when China's Chang'e 6 landed inside the South Pole-Aitken basin, scooped up rock and brought it back. First physical samples ever from the hidden hemisphere. When combined with Grail's gravity maps, these new samples reveal that the far side's upper layers are actually cracked and porous like a sponge. Furthermore, beneath the massive South Pole-Aitken basin, material from the moon's deep mantle lies closer to the surface than anywhere else. This raises the question of what else might be hidden under the lunar surface. Because the moon has no atmosphere or weather, it is easy to assume that it is entirely bone dry. But that is only partially true. Near the lunar poles, there are deep craters where sunlight never reaches the bottom, creating cold traps where temperatures drop below -400 degrees Fahrenheit. These permanently shadowed regions are cold enough to freeze any moisture that arrives and preserve it indefinitely. To test this theory, NASA's LCROSS mission deliberately crashed a spent rocket stage into one of these dark craters in 2009. A second spacecraft then flew through the resulting debris cloud to analyze the kicked-up material, and it found something extraordinary: water ice. Rather than just being a potential resource for future astronauts, this ice is an unexpected scientific treasure. Preserved in permanent darkness for billions of years, it acts as a frozen time capsule of the early solar system, containing primordial water that no longer exists in this form on Earth. Although the moon formed from the same cloud of material, its two halves look vastly different, simply because one side faced a much warmer neighbor. The proximity to our young, hot planet kept the near side soft, while the freezing distance allowed the far side to cool and become rigid. This phenomenon of tidal locking is not a rare cosmic anomaly, but rather the default across the universe. Just like the major moons of Jupiter and Saturn, and Pluto with Charon, Earth and the Moon remain locked together, each keeping the same face. Thanks to the mirrors left behind by the Apollo 11 crew, which we still bounce lasers off today, we know that the moon is gradually drifting away from us at a rate of 1.5 inches per year. The very same gravitational forces that keep one face locked toward Earth are also slowly pushing the moon farther away. As that distance increases, the moon's tiny optical wobble will gradually shrink, reducing how much of its surface we can glimpse from Earth. Now, the half we once dismissed as dark has transformed into the single most competitive target for every major space program on Earth. Missions like China's Chang'e 7 and America's Artemis 3 are converging on the exact same South Pole craters, driven by the desire to uncover the ancient ice trapped within that permanent darkness. Beyond geopolitics, the far side offers a profound scientific sanctuary. It is the only place in the inner solar system entirely shielded from Earth's overwhelming radio noise. Without the interference of cell towers, Wi-Fi, or satellite chatter, a telescope parked in this silence could literally listen to the cosmic dark ages, capturing signals from before the first stars ignited. What we dismissed as the back of the moon is becoming the front page of the next 50 years.